Hello everyone, once again welcome to our physics class. Hope you all are fine over there. Children, in the previous session we had discussed about LCR series circuit. It is one of the most important type of AC circuit. Some more topics are left with the LCR series circuit. That is, we didn't calculate the power associated with an LCR series circuit. And we didn't discuss the applications of LCR series circuit too. So today let's discuss the expression for average power associated with the LCR series circuit. Also, let us discuss about the resonant condition occurring in the LCR circuit. So let's get started with today's session, my dear children. Children, let's continue with our chapter 7, alternating current. Today we are going to discuss about resonance of an LCR series circuit. So what do you mean by resonance? You had already studied about resonance in your class 11 physics. Resonance is defined as the tendency of the system to oscillate at greater amplitude at some frequencies than at others. It is common among the systems that have a tendency to oscillate at a particular frequency, and that frequency is known as natural frequency. So what do you mean by natural frequency? See, consider a pendulum. If you leave that pendulum of its own, it will oscillate with some frequency, and that is the natural frequency of the pendulum. Okay, but if you push that pendulum with some force, it will start to oscillate with greater amplitude. So that is the resonance condition. Okay, so whenever a system oscillates at greater amplitude, at maximum amplitude, at that time the system is said to be in resonance. And when this happens, that means when resonance condition occurs in a system. When do this condition occurs in a system? See, when the frequency of the force that we have applied to the pendulum becomes equal to the natural frequency of that pendulum. That means whenever the frequency of applied force becomes equal to the frequency of the system, natural frequency of the system. So similar situation is experienced with the swing also. Okay, then suppose you are studying for your exams. Okay, so during exam time you will study and prepare more than at other days. So your exam dates force you to do that, and your studies are at resonance. Okay, so that is something about resonance. See, some examples are there for resonance. A pendulum oscillates at its natural frequency. If a push is given to the pendulum, its amplitude increases. So this frequency with which the pendulum oscillates with a greater amplitude is known as resonance frequency. That means the frequency for which the resonance occurs is known as the resonant frequency. The same case is observed in the case of swing too. A child, when sitting on a swing, swings at his natural frequency. But if someone gives a push to the swing from the behind at the same frequency with which the swing was swinging earlier, then the amplitude increases. This condition is known as resonance, and frequency is known as resonant frequency. Okay. Now, just try to find out an expression for the resonant condition of a series LCR circuit. So at resonant frequency, amplitude must be maximum. That is the condition for resonance. Amplitude of oscillation must be maximum. And in LCR circuit, current amplitude is given by Im equal to Vm by Z, isn't it? As per Ohm's law, we know that current I is equal to V by R. So for an LCR circuit, current I is Im, and for LCR circuit, voltage V is Vm, and at the same time resistance is denoted by the impedance Z. For LCR circuit, what is the expression for the impedance Z? Expression is square root of R square plus XC minus XL whole square. Yesterday we had studied this expression. Okay, so what is the expression for Im now? Im is equal to Vm by Z. So instead of Z, substitute this expression here. So you will get Im is equal to Vm divided by square root of R square plus Xc minus XL whole square. Now at resonance, our current amplitude must be maximum. So if current amplitude is to be maximum, then that means Im should be maximum. Z, that is the quantity in the denominator, should be minimum. And what is the condition for Z to become minimum? Here in this expression, when Xc is equal to XL, impedance Z will be minimum. Why? Because when Xc is equal to XL, Xc minus XL will be equal to 0. So when Xc minus XL is 0, then what is left? We are left with Im is equal to Vm by R, isn't it? Because we know that Im is equal to Vm by square root of R square plus Xc minus XL whole square. So if Xc minus XL is 0, then we have Im is equal to Vm by square root of R square. Square root of R square is R itself. So Im is equal to Vm by R. Okay. So at this condition, the current amplitude is maximum because Z is minimum. So what is the condition for maximum value of current? Condition is Xc is equal to XL, because only when Xc is equal to XL, Xc minus XL term will be 0 and current amplitude Im will be maximum. So this is the condition for the maximum amplitude of current in an LCR circuit. So maximum amplitude means it is the resonance condition. So what is the condition for resonance in an LCR series circuit? Xc is equal to XL. Now substitute the expressions for Xc and XL. What is Xc? Xc is 1 by omega c. Okay, we had studied it in the previous expression. So Xc is 1 by omega c and XL is omega L. So we can write Xc is equal to XL can be written like 1 by omega c is equal to omega L. Then from this, what is omega? See, 1 by omega c is equal to omega L, isn't it? Now bring this omega to this side. So we will, and bring this L to this side. So we will get 1 by LC is equal to omega square. And what is omega? Therefore omega equal to square root of 1 by LC. Or we can write omega equal to 1 divided by square root of LC. So this is the condition for resonance, or this is the resonant frequency of an LCR circuit, and resonant frequency is denoted by omega naught. So omega naught is equal to 1 by square root of LC, and we are getting an expression for this resonant frequency from this resonance condition. Xc is equal to XL. Okay, so what is resonance? Resonance means the condition when the amplitude of the system is maximum. Amplitude of oscillation of any system is maximum. So here in the case of LCR series circuit, we will consider resonance as the condition in which the amplitude of current is maximum. And we know that current Im is equal to Vm by Z. So if current amplitude Im is to be maximum, then Z should be minimum. And what is the condition for minimum Z? Xc equal to XL. So Xc is equal to XL is the condition for resonance. And when you substitute the expression for Xc and XL, you will get omega frequency is equal to 1 by square root of LC. And this is considered as our resonant frequency. So you should remember the expression for resonant frequency for an LCR series circuit. What is the expression for resonant frequency for an LCR series circuit? It is 1 by square root of LC. So this graph clearly shows the resonance. See, you can see this is omega naught. So at omega naught, that means at resonant frequency, the amplitude is maximum. For all other frequencies, amplitude decreases on either sides. Okay, so whatever be the condition, the amplitude of the current is maximum only for this particular value of frequency, that is the resonant frequency omega naught. So resonance is exhibited by a circuit only if both L and C are present in the circuit, isn't it? Why? Because resonant frequency omega naught is 1 by square root of LC. So resonance is exhibited only if both L and C are present. Only then the voltages across L and C cancel each other, because the voltage across L and C are out of phase, and the current amplitude is Vm by R. So the total source voltage appearing across R. Okay, this means that we cannot have resonance in an RL or RC circuit. We can observe resonance only in an LC circuit. Okay, because only in LC circuit there is a possibility for voltage being out of phase, and the current amplitude is Vm by R, which is the total source voltage appearing across R. The impedance will be minimum in that case. Okay, so current will be maximum. Now what are the important applications of resonance? So the most important application of resonance is the tuning circuit of radio. Okay, so again we can say this is one of the application of LCR series circuit too. So inside the radio you can see an LCR series circuit. So you might be listening to FM channels such as 108.4 or 91.9, like that. So to listen to a particular channel, you must tune to that frequency. For example, if you want to listen to Radio Mango, you must tune your radio to the frequency of 91.9. For other frequencies, we can't listen to that particular FM channel, Radio Mango. Okay, so we are basically changing the capacitance of LCR circuit while tuning. How? You may know, one antenna is there for the radio. This antenna receives signals from the multiple stations, isn't it? So antenna has signals from different stations like 91.9 or 94.3 or 108.4, like that. So when we are moving the knob of the radio, the capacitance inside the LCR circuit is changing actually. When the capacitance changes, the frequency also changes. Why? Because frequency omega is 1 by square root of LC. So when capacitance changes, the frequency omega also changes. And when this frequency changes and matches with any of the above frequencies, that means 91.9, that means when we change the knob of the radio, the value of this capacitance changes. So the value of frequency also changes. Suppose the frequency value initially, suppose it was 90.9. So in order to listen to Radio Mango channel, we need to get a frequency of 91.9. So for that we need to change the capacitance. By changing the capacitance, we can change the value of frequency, and when this frequency value becomes 91.9, okay, when we tune the circuit, the frequency value changes from 90.9 and finally it reaches the value of 91.9. When that frequency reaches 91.9, what happens? Resonance occurs. Okay, because when we tune the frequency of that tuned circuit and the frequency of that radio channel, both are equal. So resonance occurs, and at resonance condition, the amplitude is maximum, so both will add and amplitude reaches the maximum, then we will be able to hear the or listen to that FM channel with utmost clarity. But when the amplitude reaches near the resonant value, sound is not clear. So you might have experienced the situation when the frequency changes even to 91.8. We are not able to hear or listen to that particular FM channel with that much clarity. Okay, because the resonance condition is lost. So this is the most important application of resonance, tuning circuit of radio or TV. Okay. Next we can discuss the power associated with an LCR circuit. AC circuit means LCR AC circuit. Okay. So consider the source voltage. Source voltage is V equal to Vm sin omega t. Then expression for current is I equal to Im. Here there is not Vm. Current is I equal to Im sin omega t plus phi. F means phi. So what is phi? Phi is the phase angle between current and voltage. And this phi determines the nature of AC circuits. So if this phi is pi by 2, then it will be a capacitive circuit. If this phi is minus pi by 2, it will be an inductive circuit. And if this phi is 0, then it will be a resistive circuit, like that. Then we also know the current Im is equal to Vm by Z, where Z is the impedance of LCR series circuit, and phi is equal to tan inverse of Xc minus XL by R. So all these details we are obtained from the impedance diagram in the previous slides. Now how will you find out the instantaneous power? To find out the average power, first we need to find out the instantaneous power. So instantaneous power P is Vi, that means Vm sin omega t into I is Im sin omega t plus phi. So that is written here. So P equal to Vm Im sin omega t plus phi. Then here just here multiply this expression with 2 and divide this expression with 2. So you will get Vm Im by 2. Then here in the bracket we have 2 sin omega t plus phi. So this in the form of 2 sin A sin B. So what is 2 sin A sin B? 2 sin A sin B is cos A minus B minus, here minus is there, cos A minus B minus cos A plus B, isn't it? So here you will get 2 sin omega t plus phi will be equal to cos A is omega t and B is omega t plus phi here. So cos A minus B means omega t minus omega t plus phi. It will be minus phi, cos of minus phi, minus cos A plus B. Cos A plus B means omega t plus omega t, that is 2 omega t plus phi. Okay, so and cos of minus phi is cos phi itself, because cos of minus theta is cos theta. So cos of minus phi is cos phi itself. So here you will get power P equal to Vm Im by 2, and instead of 2 sin omega t plus phi, you can write cos phi minus cos 2 omega t plus phi. Okay, then what is average power? Average power P is equal to 1 by t integral 0 to t p dt, and we had already found out the expression for P. So it's a substitute that expression here. So when you substitute, you will get average power P equal to 1 by t integral 0 to t. Instead of P, substitute the expression for P, Vm Im by 2 into cos phi minus cos 2 omega t plus phi into dt. Now after simplifying, you will get Vm the average power P equal to Vm Im by 2 into cos phi. So After simplification, you will get Vm Im by 2 is constant, so take it outside the integral. Then we are left with power p equal to 1 by t, Vm Im by 2, integral 0 to t, then cos phi dt. Here, integral of cos 2 omega t plus phi will be 0. Okay, integral of cos 2 omega t plus phi will be 0. So, no need to substitute that expression. So, here you will get 1 by t, Vm Im by 2, 0 to t, integral 0 to t cos phi dt. Again, cos phi is a constant, so take it outside the integral. So, you will get 1 by t into Vm Im by 2 cos phi. Then inside the integral we have dt. And whenever you integrate dt, you will get t, and when you substitute the upper limit, you will get capital T minus lower limit 0. So, t minus 0 will be t itself, and this t will cancel. So, average power p is equal to Vm Im cos phi by 2. Okay, that means Vm Im cos phi by 2. So, this is the expression for average power for an LCR circuit, and cos phi is the power factor. Okay, cos phi is power factor.